All right. So yeah, so we left off on 2D, where we had the confidence interval for the slope. So we only had a few parts left, actually. And as a quick reminder, we were looking at this data set on the Great Lakes. Okay, again, the buoy measurements, and we were looking at how we can use multiple predictors now to model the peak wave height measured by the buoys. Okay. And let's see if we actually had interpreted the. Okay. So yeah, we interpreted the slope, the confidence interval for the slope. This was just a simple linear regression model. So we can see from the results here, we just had one predictor wind speed we were using. But this was the first time we'd practiced interpreting the confidence interval for a slope. So that's what we did here. And then, so we finished that part. So for E, oh, okay, yeah, we're going to get predicted values using PROC PLM, which I think stands for post-linear model fitting. I think it's kind of funny how SAS describes it in the documentation for this, because they say it is, how do they word it? Oh, yes. SAS costs money, right? So I feel like their developers are somewhat salespeople. So they say PLM offers the most advanced post-processing techniques available in SAS. It allows us to get predicted values, which is useful, I guess. I don't know if I would call it some of the most advanced techniques available, but so we're going to use it here to get predicted wind speeds if we, or predicted wave heights if we had wind speeds of 0 and 25 knots. Okay. Then we're also going to get a 99% prediction interval for that. So to do this takes a few, it's a somewhat of a multi-step process. Okay. So first, okay, first you have to fit the model. So we've already fit the model before. We're going to just copy that code from 2A. Okay. And the thing is, when this is fit previously, it's sort of like it gets the output and it prints that for us, but the model fit itself is sort of lost to nothingness after that. It's not like stored anywhere. So you can't call on it to get predicted values directly. But if we add this statement, so this was just copied directly from part 2A. Okay. We can get rid of the confidence intervals part, the plots equals diagnostics part. Okay, we don't need that for this step here. Okay. So this statement will just fit the GLM. Make sure you'd run everything above this part to import the data. Otherwise, you'll get an error saying like cannot find Great Lakes data. So if we run everything above beforehand, then we should be able to run this, and we'll see how this just fits the model. Gives us this output. Okay. But again, nothing is stored. So if we want to be able to call on this to get predicted values later, we have to add this statement store. And then you get to call it something. It's like the name of the model fit object that we're storing. So here I like to use camel case, where you separate the words by just the capitalization of them. It's called camel case because it's like the humps of a camel going up and down. So I called it my model fit, but you could call it anything as long as it's a valid SAS name. So SAS names just like cannot start with numbers. It can't use periods or other special characters like that. You can use underscores, but there's some constraints to it, but this is the idea. So now if you run this, you should see pretty much the same output. Okay, nothing really changed, but what happened is it stored this my model fit object in memory now. So now it's available to call on to get predicted values. I don't think it shows up in libraries, but maybe it does. No. It's somewhere hanging around. I don't know where it is, to be honest, but there's some way in which you could see where this object is at. Okay. But that's the first step. Okay. The next step is to create a data set that has the predictor values in it that we want to get predictions for. Okay. So here, for example, we want to get predicted wave heights when the wind is 0 or 25 miles an hour. So we have to tell SAS that we want it at the values 0 and 25. Okay. So to do that, what we're going to do is make a new data set that mirrors the structure of our original Great Lakes data. Okay, so we're going to call this like pred data for like prediction data. Okay. And this is what's called a data step. So here we are making data to obtain predicted values. And actually what we're doing here is sort of like the old-fashioned way of data entry in SAS. Like, you may still do this sometimes nowadays, but it's probably much less common to manually type out a data set, like enter the values into SAS directly. This is how people would do that. So you use this, what's called a data step, where you're picking the name of the data set, and then you have this input statement, which is where you tell SAS what the names of the variables are going to be in the data set that we're creating. In this case, we want it to be exactly the same as the variables that were used in our model from the original data. Okay. So we used, we renamed them. So we used wind speed and wave height. Those are our two variables. Okay, so we need wind speed and wave height. It's important that these match. The capitalization case is not important for variable names in SAS. It's what we call case agnostic, but it is important that this is spelled the same otherwise as in our original data. So we're saying we want to create variables called wind speed and wave height. And then what we're going to do is, there's a few ways to do this. In SAS, you have to give it a heads up like, oh, I'm going to input the data now by saying data lines, colon, where am I missing a colon? No, that looks how it is. Okay. Oh, yeah, that's fine. Okay. And now what we're going to do is we're going to give multiple rows where each row corresponds to a row in this new data set that we're making. So we're going to give a value for wind speed, a value for wave height, and then hit return for the next row in the data. So for wind speed, we want a 0 wind speed. And the thing is, we're getting a predicted wave height, so we input a missing value for the wave height here. And missing values in SAS are given by a decimal, a period. So then we want a wave or a wind speed of 25 knots, and then a missing value for the wave height. Okay. And then to say we're done entering data manually, we do a semicolon, and you should see the coloring is all squared away for this data step now. You can think of this is like filling in the values in an Excel spreadsheet. That's essentially what we're doing here in a difficult way, right? This was before Excel, so. And this is a way to do it such that you can have everything contained in your SAS program, right? All right, so we should be able to run this. It doesn't produce any output directly, but I think SAS Studio opens up the data set when you make a new one. Yeah. You should be able to see this new data set. Okay. Any questions about how this data step works? I know it's a little bit new. You know, if you go on into more classes that use SAS, you'd see it more. Yeah. Oh, you have an error right now? Yeah, let's do that. Mostly it's importing the data, like creating that data. Yeah, expecting that number. Yeah. Yeah, and then we'll also run the yes. All right. So we have this data now. Okay, and if you look at it, you can see how it has wind speeds, but the wave heights are missing. So then we're going to call on SAS to say, hey, use that linear model that we fit before, my model fit, to fill in the values here for the wave heights. Okay, we're going to get predicted wave heights that way. So how we do that is this process of, I wasn't familiar with this terminology, to be honest, before I read the SAS documentation. This process of filling in these values that are missing with predicted values is called scoring a data set. That's what the SAS developers call it. Okay. So we're going to score that data set here. And so we are going to calculate and save predicted values and intervals and prediction intervals. We want to be specific. So now we're using that as they described. Some of the most advanced techniques in SAS. Okay, so buckle up. Proc PLM data equals, oh, not data equals yet. We're going to say proc PLM restore equals my model fit. Okay, so the important thing is this matches what was in the store statement. And then since we want a 99% prediction interval, we're going to say alpha equals 0.01. Semicolon. And then, so we're saying we want to use this model fit. We want to get 99% prediction intervals. And then we're going to say, which data do we want to use to get the predictions? So we say score data equals red data, where this has to match the name from here that we created for the data set. And then this next statement, we say out equals, and here we're creating another SAS data set that will then have all the predicted values and the prediction intervals in it. So this is again where we get to pick the name of a SAS data set that we're creating. So I just called it fit data because now it has our fitted values. And I like to use camel case myself. So no semicolon on either of these lines. And then now there's a lot of different things that it can output from the predictions or associated with the predictions. If you want to have a column in this new data set that has the predicted values, we add predicted. We're also going to add a confidence interval for the mean response value, which is LCLM for lower confidence limit for the mean. UCLM, which is upper confidence limit for the mean. LCL, which is a lower confidence limit for the prediction interval. And then UCL, which is upper confidence limit for the prediction interval. Okay. And since these are like, yeah, a lot of acronyms, and it's kind of hard to keep track of, I added a comment in here saying what's going on in this code. So asking SAS to save. And then we have LCLM, which is the so just for your future reference, if you come back and look at this code, chances are, if you're like me, you won't remember what LCL UCLM stands for like a year from now. So this is where comments are helpful to tell your future self, like, what is that doing again? Oh, and I forgot that predicted is the predicted value itself. And then we close that off like we do every proc with a run statement. Anybody have any issues with that code? Go ahead and try and run it. Bless you. And we'll see. It doesn't print the predicted values for you. You should just see something like this. Yeah. And then to see the predicted values, okay, so we created this SAS data set called fit data. So if you look at the output data tab, bless you, we see here, you can drop down here and look at different tables of data. Okay, here we can see the fit data object. And now you can see it has the predicted values, the confidence limits for all those intervals that we just asked about. Okay. Show the code again. So if you want to display that in the results output, we can use a proc print. Data equals fit data. Okay. Now if we run that, there's our predicted wave heights. Yeah. Oh, okay. Yeah, let's check it. It's probably a it's one semicolon after the top of that, and then oh, okay, just an equals off the top of it. And then years. My models fits. Okay. Let's see. Okay, let's run by setting into this. And that will like create that my model fits. Or yeah, that one. Yeah, you can. Nice. Or no, there's an error. My model fits. Okay, let's go back to the code. Let's just run 72 cases. Take that one so that one here. Oh, okay. So for that, let's run at the top of our script. So it's saying it can't find the Great Lakes data. So often that means we just need to import it. So let's how does our code look again? Down at the bottom where the model fit is. We have Great Lakes new. So let's we scroll up to the top. Let's run line 27 on up the top. Yeah, let's see if that runs down there. Okay, so that probably just needed to be run. Now I bet if we run that model code. Yeah, that one will run. Yeah. SAS just doesn't remember, so we have to rerun that. Yeah. Yeah, let's try to be running again. Okay. Then let's see. Yeah, let's try to run the 111 through 108. That's the one where we create that. That probably has its own error. Yeah. That's
oh, I missed it.
yeah.
Okay. Okay, thank you.
Yeah.
I also have so I have mine. Did that here.
Okay, yeah, let's let's try to run just so it says it can't find my model, but let's run like line 86. We did top of that graph. Okay, so underlining the part where it doesn't like it, and I think I can see there that there's like semicolon missing. Yeah, semicolons are always the most annoying thing in SAS. They're hard to figure out when one's missing or not. Okay. So we got our predicted values. Always good to look at them and see. I think I mentioned this before, that it seems reasonable. So wind speed of 0, it's saying it predicts the peak wave height to be about 0.03 feet. So pretty much no waves. That checks out, right? And then 25 knots, which is roughly 29 miles per hour. So very, very windy. It's saying the peak wave height is about 5 feet, which is really tall for the Great Lakes. So that seems reasonable, right? Right. So okay, so we did do that part. Indicate in a SAS comment what our predicted wave heights are. Okay, so now I'm just asking for the values. So that is 2F. We'll just say when maybe we'll word it like this. So the predicted wave height or the predicted wave height when the wind is 0 knots is 0.03 feet. And the predicted wave height when the wind is 25 knots is about 5.0. I remember when I was an undergrad, I always used to like to write out a lot of decimal places because I thought it was cool that the computer could tell us that far out. But I've mentioned this before. Somebody pointed out to me how they said, like, if you use too many decimals, it implies almost more confidence in your estimates than you actually have. Like, can you actually be that certain, like out to that many decimal places? Probably not. Probably out to like 1 or 2 decimal places, given the size of the data set, is about as far out as we can say. So here, I think 2 decimal places is reasonable. And honestly, I don't think anyone cares if the peak wave is going to be 5.001 or 5.002 feet tall. There's not really a meaningful difference there. So, okay, so the last thing we're going to do is interpret these prediction intervals. Okay. So prediction intervals are useful because you can get a predicted value using a linear model in SAS, right? But it's also really important to be able to describe the uncertainty in that prediction. Okay. Like we predict the waves are going to be as tall as 5 feet when it's 25 knots for the wind speed. But would we be super surprised if the waves got up to like 10 feet? Or is it, we're really confident it should be between like 5 and 5.5 feet? You know, that range of values for which we think it could fall into is important to describe. And the single value is useful as a predicted value, but describing that uncertainty sometimes is just as important. So that's where the prediction intervals can help us. Okay. So let's see, 2G I ask. Just for the prediction interval. Yeah, so for the prediction interval, let's get let's list out the bounds, the lower and upper bound first. Okay. So from here, which numbers, let's see, for 0 knots, what are our, for 0 knots, what are the lower and upper bound for the prediction interval? Here.
-3.6 and +3.7.
Right. Yeah, right here. Thanks. All right, so to interpret this in general, or maybe I'll start with like a blueprint interpretation up here. So if you have a prediction interval like this with lower bound and upper bound, you can say we expect the response variable to be between, and we'll say this is a 95% prediction interval since that's most common. We expect the response variable to be between LB and UB 95% of the time. That's the phrasing for interpreting a prediction interval. So notice nearly always for confidence intervals in statistics, we have to use this phrasing of like on average. But the prediction interval is very much not about the average. It's about individual values. Okay. In the wave heights example, it's a very important distinction, because if you are predicting the peak wave height, the tallest wave that the buoy will observe, okay, you can get a confidence interval for the average wave height on a day with a given wind speed, which will be, if you look at all the waves that day that come in, calculating the average of their height as they came in. That's very different than an interval for the individual wave heights. Because if you think of like the see if I can get a picture. Right. Okay, so has anyone been to the Grand Haven Pier out here? Right, it's a really nice area. So if someone was trying to like model the tallest wave heights, right? The idea of what the average wave height for a day is not very important. Like it doesn't matter where the tallest wave was on average throughout the day, because it only takes an individual wave to like crash over the top. So that's more what we're interested in here. The prediction interval is what describes the range of heights for individual waves. Kind of like statisticians have like a joke about some statistician like drowning when they crossed a river that was only like 2 inches tall on average, or 2 inches deep on average. But it's like, it more matters what the individual most extreme value was, not the average. So in this case, the prediction interval is much more important. Wait, is that what we got though? Oh yeah, it's for 0. Okay. So this is our prediction interval, which is what we're much more interested in than the confidence interval for the mean. And so we can interpret this by saying we expect the peak wave height well, I guess we can say units up there. We expect the peak wave height to be between this number and this number feet. And then this was a 99% prediction interval, I think. Yeah, we did a 99% interval. So and then how could we fix up this interval to be more practically useful? Probably more sensible.
Say 0.
Yeah, you say 0. You don't. We won't say negative numbers because that's can't really have a wave that's negative height. I mean, I guess I don't know. Yeah, we'll just say you can't have a wave with a negative height. Doesn't really make sense. Okay. So a very simple model, but maybe if we were like trying to set safety guidelines for like the Grand Haven Pier, we'd say like, oh, if the wind is just 0 miles per hour today, seems like 99% of the time we would expect at most a 4-foot wave about. So if the pier is like well above that, maybe we'd say you can have like, you know, people on the pier. It's safe that day, right? What about for 25 knots? So let's do the same thing. But for 25 knots, we have, these are the two values, right? LCL and UCL. Oh, you know what? I've forgotten the phrasing. When we have to say what the predicted value is, that's important. So when the wind speed is 0 knots. Okay. Yeah, sorry, make sure to add that. That's important. And then here we'll say when the wind speed is 25 knots. Okay. So not surprisingly, when it's really windy, we can expect larger waves potentially. Sounds like up to 9 feet. So maybe if the pier is only 8 feet above the water, This implies that if the wind is this high, maybe they should not let people on the pier because it's not safe. Right. Of course, you would need a much more complicated model than just using wind speed. Hopefully, you would use something that's more accurate. And also, maybe 99% confidence is not even high enough, because if it's for people's safety, maybe you want like 99.9% confidence or something like that. Okay. There'd be some trade-off, I guess, between people's enjoyment of using the pier and safety. So, but this could help us maybe make an informed decision. Right. Any questions about those intervals and how we interpret them? So nearly always you want a prediction interval rather than a confidence interval for the mean response, because like I showed how to get it here, but these intervals are going to be centered at the same value. The middle of the interval for the prediction interval and the confidence interval for the mean are always the same. But what do you notice is different about the intervals themselves? Yeah, the range is smaller for the confidence interval for the mean. Okay. And actually, if you had a bigger and bigger sample size, the confidence interval for the mean will converge to centering around a single number. It'll get more and more narrow. But this would still stay wide because it's talking about individual waves. And there's always going to be variability in individual waves, no matter how big your sample size is, because that's just how the data is. But this is giving the average wave height across a day. And so the idea is that if you have a bigger and bigger sample size, you could be more confident in what that true average actually is. So this interval would get more and more narrow. But they both describe different things. So you have to be careful with which one you're using. Nearly always, for like most contexts, you're looking at the confidence interval or the prediction interval. That's what you're interested in pretty much always. So, okay, so that was still simple linear regression, but we hadn't seen how to get predicted values or prediction intervals in SAS yet. Now we're going to do the same thing, similar concepts, but for multiple linear regression. So we will model the wave heights still, now using the wind speed and temperature, okay, which we saw in an activity already. We're just doing it in SAS now. Okay, so 3A. And let's get diagnostic plots. Okay, so let's copy the code from 2A, I think it was. Yeah. Let's copy the code from 2A again. Okay. And now we're using wind speed and temperature as predictors in this model. And we want to include the interaction between them as well, which we haven't talked about interactions yet. I don't think we'll get to it this semester, but if you go on to take Stat 321, you would learn about interaction terms in models. But to include an interaction term, you do an asterisk and then the name of the other predictor. So we want an interaction between the wind speed predictor variable and the temperature predictor variable. Okay. And then just to be clear, we'll also have what we call the main effects of the predictors in the model as well. Okay, we'll get rid of this alpha, and we'll get rid of the CL parm. We don't need that anymore. It wouldn't hurt to keep it in there, but let's get rid of it. And we're going to end up getting predicted values from this model as well. So we're going to add that store statement again. And now since this model has an interaction term, maybe we'll call it interaction model, something like that. Okay. Okay. So this is a more complicated model. We're now accounting for the temperature and the interaction between wind speed and temperature to predict the wave heights. We look at that output. Okay. Now you get a regression estimate for temperature, one for, oops, no, here's the estimates. A regression estimate for temperature, wind speed, and then the interaction between wind speed and temperature. Yeah, here's the diagnostic plots. Okay. I don't think I asked how they look. So I guess real quick, how does we check the model assumptions in the same way as before, right? How does normality look here? It's not the worst I've ever seen, but it's the QQ plot is a little problematic. There's a lot of points that are off the line. And the histogram is okay. It's kind of questionable, but again, not the worst, maybe. If we look at like the residual by predicted value plot for homoscedasticity, how is homoscedasticity looking? Yeah, if we think about, I guess this point is kind of throwing things off because you could say it looks almost like this, in which case it's an outward fanning shape. But it is kind of tough because it's almost like that one point is what's dictating that idea about how it looks, because if you took out this point, it maybe looks more like, it's still a little fanning, I guess. Yeah, I would say it's fanning outward, so it's homoscedasticity is violated here. The spread is getting bigger for bigger predicted values. Also, just as practice, I guess, do we have any influential points in this data set? So we look at Cook's distance value for influence right over here. And what's our cutoff again for that? So the SAS developers draw this horizontal line here. I don't know why or how they pick that value, to be honest, but we use 0.5 because some professor at Penn State says that's a good thing to use. Honestly, that's I had to search around. It's hard to find. It's not as easy as like the p-value compared to 0.05, but we compare to 0.5 in this class. So All these are actually below that. So we're not concerned about influential points here for this data set. Yeah.
Which one do you use to find outliers?
Yeah, for outliers, we look at the studentized residuals, our student. So you could look at either of these two. I usually say to look at this one. And we align with the SAS developers here. So we use 2 as the cutoff for the magnitude. Right, so if points are below -2, it's an outlier. So this is an outlier. And if they're above 2, it's also considered an outlier. So this has like at least 5. It looks like there's like duplicate points overlapping here. So there's more than 5 outliers. Okay. And then the last thing, I guess, to mention from this output, there's a lot of things to talk about from this output. Okay, notice that it gives us the R² value right here for the model. Okay, and that's something we know how to interpret, right? So an R² of 50 of 0.505. How do we interpret that for this model? So anybody want to give a crack at it? What can we say? Oops.
Would it be moderate?
Yeah, you could talk about like strength of correlation between the predicted and response values. Here, R² has this really nice interpretation. Did you want to try?
Forgot how to start. It's like our model accounts for like 50% of the variability.
Right, yeah, it's all about talking about how much variability our model explains. So our model explains roughly 50.5% of the variability in Y. In this case, that is in the peak wave heights. Right. And instead of saying the model, you can say, or it's good to be more specific, like this is correct, but we can say like the names of the predictor variables. So wind speed and the water temperature, like that. Okay. So this may seem like pretty low, but actually for real data, I mean, sometimes your R² is not super high. It really depends on the context. Something like wave heights, the thing is that there's probably many factors that influence how tall the waves are in the water, besides just the wind speed and the water temperature, right? That we don't have measured here. So that's how we could interpret R² here. Okay. And yeah, we haven't really talked about interaction terms much, but taking a statistician's perspective of regression modeling, which is what we do in this class, when we decide to keep predictors in our model or not, if you have an interaction term between 2 predictors, you first start by considering dropping the interaction. Rather than, you wouldn't consider dropping individual predictors. but keeping the interaction. Okay, you have to just consider the interaction. So here, the p-value is for a test of whether or not this slope for this term is actually 0. Where a slope being 0 would mean that term's not important to include in the model. So what does this p-value tell us about the interaction? Does it seem like we should keep it in the model?
Yeah.
Yeah. So small p-value means it seems like it's important. Okay. We have the overall f-test is very significant, has a p-value that's very small. And then if we were looking to trim down the model, still some more, since this p-value is so small, that implies we should keep the interaction term in the model. Like I said, we might get to an interaction activity, but I don't think we will have time before the end of the semester. So, okay, so we'll consider fitting a model though. Like we'll pretend this p-value is bigger than 0.05 or bigger than 0.15. Just that it was bigger and that we needed to drop the interaction term. We'll pretend that happened. And yeah. Okay, so we'll just fit the model with just the 2 predictors, but no interaction term. Okay. And we'll call it like 2 cred model for 2 predictor model. So we copied the code and pretty much just took out the interaction term and renamed the model fit that we're storing for 3B. We run that and we get, these are our results now. Ironically, the normality actually looks better now by dropping a term, which is kind of surprising to me, to be honest, but usually that doesn't happen. But normality looks a little better now. Homoscedasticity also maybe looks a little better. Yeah, it's not very often that like dropping predictors will improve the model assumptions. I think that's kind of surprising in this case, but that's what happened. Still no influential points. Okay, nothing above 0.5 in the Cook-Stee plot. Studentized residuals. Yeah, it looks like we actually have less outliers now. We still have some, but there actually seems to be less. So model assumptions improved. Right. SAS gives you this, what's called a contour plot. Okay, so it's showing, essentially this is a plot that shows 3 quantitative variables simultaneously, which is, it's always a little bit difficult as you get more and more variables to visualize it. They're using temperature as the y-axis, wind speed as the x-axis, and then the color is being determined based on the wave heights. Okay. So blue coloring is lower wave heights, red coloring is higher wave heights. You can see as the wind speed gets higher, the waves are getting taller, which makes sense. And then you look at temperature, as you like fluctuate temperature, it seems like at a given wind speed, temperature doesn't seem to influence the peak wave heights very much. Okay. Yeah, I can show. Did you need to see the code again?
Our 2 plots are the same.
But like yours are like straight, like up and down.
Oh,
It's because we changed a little bit.
do you have the interaction term still in the model?
Yep, yeah.
Yeah, so the interaction term,
This should just be.
Got it.
Thank you.
yeah. So yeah, the interaction term would allow, without the interaction term, what's happening is our predictions assume like a constant effect as you move horizontally or vertically. But with the interaction term, it would allow it to have, yeah, if you look at the contour plot with the interaction term, it allows it to move in a not just straight, or like it can move differently depending on the interaction between temperature and wind speed. In this case, yeah, I guess it doesn't really seem like, based on this plot, I don't see anything to me that makes it clear an interaction term is needed. Okay, mostly it just looks like if the wind speed is really high, the waves are high. It's kind of not a very complicated relationship in that way. Okay. Okay. So kind of what we're doing here is we're pretending again, maybe we want to have the most accurate prediction of wave heights possible because we're setting safety standards for the Grand Haven Pier, something like that. So there's all these different models you can consider. Just the single predictor model that we had before, just wind speed. We had this 2 predictor model with the interaction term, or just a 2 predictor model. And then we can also, we'd considered a quadratic regression model in a different activity where it was wind speed squared. So we can also fit that model. So we'll do that here for part C. This is kind of how predictive modeling goes. You often fit many different, we'd call them like candidate models, like models you could use for your predictions, and you try to pick which one you end up using. Okay. So for the quadratic, we do get rid of temperature, and now we have wind speed times wind speed, and we'll call it like quad model for quadratic. So if we run that, okay, again, actually the normality looks okay here for the quadratic model, not super bad. Homoscedasticity looks fine. Oh, the other assumption we didn't talk about was independent errors. I guess I forgot to mention that one. How does independent errors look here? It's pretty okay. I could see the argument of someone saying there's like a negative relationship in the residuals like that, but it's not super strong. So I think it's okay. Yeah, there's outliers. Okay. Here's the implied quadratic fit. It looks decent. It looks like it's capturing the trend okay. So this is where it gets tough because all these models are very similar. They perform very similarly. It's like, which one should you use, right? And we talked about this before, like the Occam's razor rule of thumb. It's not that you should always include more terms in the model. That's not necessarily going to be helpful because if they're actually not important, they'll make the predictions worse for data that's out of sample, for new data that you haven't seen yet. So yeah, how can we get the best predictions possible? Because we want to have the best safety recommendations for the pier. Okay. So one way to do model selection is to look at the adjusted R squared, because R squared will always be higher for the more complicated model, for the model with more terms, more predictors. but adjusted R squared penalizes if those predictors are not important and we're just including them in the model. Okay, so to do that, to get the adjusted R squared for each model, what we're going to do is for 3D, we're going to use proc GLM select. Okay. And then say data equals Great Lakes clean. Model, say response variable equals, and then when you're using proc GLM select, you give it the most complicated model you're considering. And what it'll do is it starts with that, gets the adjusted R squared, removes the predictor, gets the adjusted R squared for that model, and goes on down until there's no more predictors. And it'll show you the adjusted R squared at each step along the way. Okay. So we can, let's see what the activity asks for exactly. Yeah, the two predictor model, the quadratic, and the single predictor model. Let's see if we can include the interaction. I don't think I tried this, but. Okay, wind speed times wind speed. Temp, and let's see if we can do the interaction between temperature and wind speed. I'm going to try this and see if this runs because I did not try this. But this is how I would do the model selection if I was doing this in SAS in real life. So yeah. Wait. Okay, yeah, that didn't do what I wanted it to. Okay, we're gonna get rid of the interaction term in temperature, I think, because I just asked in this activity for. Oh no, I did ask for the interaction. Okay, interaction to predictor and the quadratic. Well, okay, here we're getting it for the. Let's see. I'll write SAS comments. So calculating adjusted R squared for the quadratic model. That's what we're doing here. And then we'll just have to make a separate call to GLM select to get it for the interaction model. Okay. Okay, so we're just getting two sets of output here. Let me see, I'll run this to be sure this gives us what we want here. Right, we have the quadratic model. Oh, I see the problem. We have. Oh, I see what I forgot. I forgot to add this slash with an option. We want to say selection equals none. Okay, so before the output was just giving the final model that it selected, but it wasn't showing the work along the way. And then we want to say select equals ADJ RSQ for adjusted R squared. We're saying we want you to use adjusted R squared to select. or to evaluate the model fits. Okay. There we go. Yeah, much better. Okay. That's what I was hoping for. So see how this one looks. Yeah, you know what? Okay, yeah, to be more concise, we'll just go with this last final call to GLM select. So we have, there's a lot of terms in the model here. It's wind speed, then temperature, then the interaction between the two, and then the quadratic term. We're considering all of these things to include in the model potentially or not. And we can use GLM select here to say essentially fit all the models by starting with everything, getting the adjusted R squared for that, dropping this term, and then getting the adjusted R squared for just these predictors, and so on, like dropping the terms one at a time, and getting the adjusted R squared for each. And that will tell us which predictors we should use in our final model. Yeah, are you getting an error?
Yeah.
So run that and think about which model it implies, looking at the adjusted R squared, which one it implies is the best model. Okay, I think we just don't have equal sector models. Yeah, I don't know. So what this does again is it just concisely shows, and it says the number of effects, that's like the number of predictors. Okay, so here's the biggest model with everything included. Here is the adjusted R squared. Then it dropped the term. So in the next row up, it drops the term that was listed below. So here it dropped the quadratic term and just has the interaction term. And then SAS nicely gives you an asterisk next to the one that says, hey, that's the highest adjusted R squared, right? Okay. So this is where you can see this effect of SAS thinks the quadratic term in here is overfitting based on the adjusted R squared. And so it thinks, okay, the simplest model that does the best is the interacting model. It likes that. It thinks it does better than the two predictor model. Enough so that it justifies keeping the interaction term. The quadratic model, it thinks, does not perform significantly better to justify including that extra term. So this interaction model it implies is our since the interaction model has the highest adjusted R squared, we select this as our final model. And I'll put in parentheses what the value of that was. All right. So that's it for this activity. So make sure to turn that in via Blackboard. I'll post a video because I'm recording this as well to Blackboard. So Yeah, that'll be all. And then next week on Tuesday, we'll talk about categorical predictors and dummy variables in regression and how that works.